the contents that I have and the material is the overfitting is, which I believe is one of the most important thing that you should know. So when you do the data analysis and AI or machine learnings or even deep learnings, and I'm going to explain what the overfitting is and discuss how we can avoid or overcome the things. And let's take a look at what the overfitting problem is. And suppose we have regression problems, and so and think about nonlinear regressions. And I mean, this one is how many data points that we have. Let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10, I will say, training data set, I mean data point. And if this is linear regression problem, and I will say, so this is input and this is the output. And I will say there are 1 x plus and the constant values. So we have 2 unknown parameters for degree of 1, because we have to think of the constant, the parameter or term as well. So just using the linear regressions, so we can easily, and we know how to do it, how to find this, how to approximate, or we can do the data fittings. So there will be, and probably, so the data is like here. So it's, I mean, if we just take a look at this approximators, probably say this is simple enough. So why don't we use nonlinear regressors to increase the complexity of the models? So one way is we can think of polynomials. So the next thing is, okay, so why don't we set like that, right? So this is quadratic polynomial equations, and unknown, in this case, unknowns are, I mean, here, sorry for the typos. And so we have 3 unknowns and we have 10 data points. And I mean, this is nonlinear regression problems, but actually this is a linear regression problem with nonlinearly distributed data points. So we can solve that, and out of this, from we can find out, we can estimate these values, and we can plug in that and plot it. So this is the best approximator with 2 degrees of polynomials, right? I mean, this one, I mean, I guess with given these 10 data points, at least for me, it looks okay or looks fine. Okay, so now I increase the complexity of my model. I will say that, or I increase the degree of the polynomials, and we can keep increasing it, right? Here, and this is the best approximator when we have, like, if we assume that our model is like that, and keep going, and 5 and 6 and 7, 8, 9. So I mean, this is, let me think about this case, because this is, I believe this is really important to have a good understanding of these figures. And now since d is equal to 9, which means it's 9th degree, right? So this is my model in polynomial models. Doesn't have to be polynomial, but I assume that it's polynomials in. Then let me ask, how many unknown parameters in this case? How many?
10.
We have 10, right? And another question that I want to ask is, how many data points are given? We have
Only 9.
how many data points?
10.
10, right? I mean, you can count it. So what we can do is we have 10 unknown parameters with 10 data points. So what we can do, actually, we can plug in these individual data points here. Then we can construct the system of linear equations, right? So we're gonna have, since we have 10 data points, we'll have 10 linear equations. Then what we can do, we can set up, so this will be so here, how do I say, 9, 8, 1, x. For the first data points, for the second data points, you guys know what I'm doing it. So we have, this will be suppose this is bit matrix of A, and you will get y1, y2. Actually, the true values, we have 10 data points. Then let me ask, what's the dimension of matrix A, or what's the shape? What's the shape in this case? What's the shape of the matrix A? What's
10
the
times
size? 10 by
10.
10, right? So in general, say it's a square matrix. So we can suppose we are able to compute the inverse of, then this is A inverse Y, which means there is unique solution exists. So this is not a optimization problem anymore. This is just system of linear equations. So always, I mean, not always, if we have, in many cases, we know that this inverse does exist, then we can compute it, so we can get exact solutions. So again, let me summarize it. If we have suppose we have, how do I say, n unknown parameters that we want to estimate it, and then we need m equations or constraint or data points. Then what we can do, we can get like this, that we can get the solutions that there's no, always we can make that happen. You see that? So let me erase these things. So for the linear regression problems, the objective functions, if you guys remember it, and say we have m data points, and this is estimated, and this is true, and we did that. And what I can do, I can make it, this one is equal to 0 always, because if I have m unknown parameters in my model, say if you have like millions of data points, then I can do this because I can set up the polynomial regressor with millions of unknown coefficient. So this one is easy to make it, but see that, let's see this one. This graph is polynomial, I mean the best approximator with degree of 9. And for each training data points, we can see that there's no difference. So this y hat and y are exactly the same. So I mean, this is the best approximators again. But let's think about what's the for regression problems. I mean, what is the ultimate goal of regression model that you guys can think? What would be the ultimate goal of regression? So think about the data points as given, and we're gonna set the models, and we can construct the regressions or the approximators, right? And the ultimate goal of this is, if we suppose we have new inputs, say here, then from this model that I constructed it, what I can do is I don't have these data points in my training data set, but based on the regression models that I established, if I have new data points when x is -2, this one will be the best prediction values that I have. So that's the meaning of the regression models. But think about here. Here, if you have, and probably this one is, but I mean, this one, everybody knows that this one, something is wrong, because we know that most of the data points are here. So again, what I'm saying is that if you allow the model or increase the complexity of the models, the model can do better job on the training data set. But on the other hand, it's gonna get worse on the new observations. We call it's overfitting problem. And in most cases, overfitting is something that we want to avoid. We don't like it. So let me take a look at this one. And when you have data set like this, and you have to split it, like, I don't know, like 70% or 30%, we're gonna use this one for trained models. We call it's a training data set. And this one, we're gonna reserve it because we want to test it. We want to test it, so for the models, we will train the models with the only training data set, and we don't allow the models take a look at the test data set. So once to build the models, we're going to use this test data set to evaluate to see whether this model is good or not. So let's compute, say this is a residual sum of squared, I mean like error squared, or you can think of y hat minus y and squared. And the red one is training loss. If you increase the degree of polynomial functions, I mean, the loss it gets smaller, right? And here, when the number of unknown parameters are same as the number of data points, as you can see, the loss is equal to zeros, which is it's good and something that we want to test. Something that we set up as objective functions in the optimization problems that I designed, which is good. But with same models, if I tested it with test data set like that, and the loss is humongous here. And you can think of this is the case. This is the case, right? So again, from these figures that we can say is that training data set, if you increase the complexity of the model that we assumed it, the loss always gets smaller. But at the same time, we have to test it, evaluate the models with test data set, see if whether it gets smaller or gets bigger. And we don't want to do this kind of things to see, because obviously this is the point that we have overfitting problems. Okay, so well, I think the best way if we have this kind of loss functions with having different degree or complexity of the models and change that complexity and plotted the loss functions based on the trained models and based on the testing data set. So probably I will say these are the good number of the model complexity that I can think of it. So let me summarize the overfitting problems. We have many times we just came across the situation that our model performs exceptionally well on the training data set, but it's not able to predict the test data set. So this is one of the most common problems that data science professionals, data scientists face to avoid overfitting problems, which we don't want. We don't want. So this is the goal of how would I say, of machine learning. Okay. So let's think about. So I will say it's rich representations. That means it's very expressive when the assumed model or our model is very expressive. That means it's a high complex, I mean, how do I say, high degree, or then there's some issues on that. If we have rich representations, then the input training data set is going to have very small errors, but in the nearby, there will be the errors, it's going to be high. That's the first thing. The similar way that we can describe is for the training data set, we have low errors, but for the testing data set, we have higher errors. So, but the focus is not here. We have to, this is our focus, right? These data points. So I will say around here, it's again, it's similar figures that you guys seen in the previous one. So it's good for training, but it's not good for the testing. So from the overfittings, probably this kind of things behavior that you have to imagine and visualize it. And for, I guess, around here is the kind of okay models that here. So let me describe new term. Instead of just saying errors, I will say generalization errors. So let's think about the objective optimization problems with objective function that we defined it for the regression problem again. So we are optimizing the parameters like that to solve. This is the previous objective functions that we defined. So this is the actual values is from the training data set, and it's already available, we know that. And this is prediction models or the approximated values, and we can define the loss functions. And for the entire training data set, we want to minimize it. So there will be the optimal solutions for that. That's how we define it. But when you think about this, this one is that, which means we want to force the optimization solvers to do best on the training data set. That's how we set up the objective functions. But when you think about the real case, what we really care about is loss of predictions on new data set. But as you can see here in our objective functions, there's nothing on any information related to new data set. So we call it generalization errors. For the best regression models, we want to minimize generalization errors instead of minimizing the errors on the training data set. That's why we need to divide it into training sets and the testing data set. Right? We wanna do best in the either validation sets or training data set. Right? That's actually somehow we need to reflect these things into our objective or loss functions. That's what we want to do. So in order to solve that kind of things, again, if you see that the titles is regularizations, that's one of the way that we can avoid or we can resolve the overfitting issues. And let me explain this. With many features, that means many data, prediction function or models become very expressive, so it's a lot of model complexity. So in general, it's not good. So basically, what we want to do is we want to have a good prediction models with, to minimize the generalization errors with, the simple models with the model, as simple as possible. Because we know that if the model is very complex, it might be overfittings. So to do that, we want to choose less expressed functions. That means lower degree of polynomials. For RBF functions, it's a fewer number of RBF, the centers, things like that. This you don't need to. This is optional. You don't have to understand. Or that's the first way that we can do. First way is to overcome the overfit. I mean, to solve the overfitting problems. I want to set my model as simple as possible. That's the first way that you can do. Second way that we can think is, this one might not be very intuitive, but here we want to keep the magnitude of parameters in this that is small. So what do you mean by this? I want to keep the values of this is very small. If you go back here, in this case, I mean, the data tends to have large values. To set these constraints. Okay, so with that, so I want to penalize large value of parameters. So we call it regularizations. So remember, this one was the objective functions, and I want to penalize. I mean, this one is minimizations. I want to penalize the large value of parameters. So again, I want to minimize it. So I want to keep as small as possible. So that's new objective functions. And since we have two terms in a single objective function in scalar values, so there is the regularization parameters. So it will be, I mean, the first term and the second terms, there's some trade-off. So this is something that I need to define, user defined. So it's another hyper parameters that I need to set. Okay. So let me see that. So often the overfitting is associated with large estimated parameters. So I want to balance it, how where the function fit the data set. That's what we used to do it. And now there's another consideration that you have to account. So it's the magnitude of coefficient. So there is now in a total cost or loss, there's two index that I want to control or minimize it. The first one is that I want to measure how the model, how the measure of fit. So I can compute the residual sum of squared, and I want to minimize that. And the second term is that the measure of magnitude of coefficient. So that's magnitude is a distance or strength or length or size of this, and this will be the vectors. So I use the norm to define the strength, or so I want to minimize this. So there's some related, and this is mathematical expressions or mathematically express the objective functions that I just mentioned it here. So I mean here, if we have, so this is multi-objective, the optimization problems is lambda is tuning parameters. If I set lambda equal to zeros, that means there is no regularizers. And if this one is extremely large, then I feel like this is almost, so I will, this one, if you have that, probably all the coefficients are, I mean, just almost zeros. So that's kind of I mean, what I did so far is that, let me summarize things as I will just raise the issues on the overfitting problems. So that's, the overfitting is not a good phenomenon that you want to see it, especially when you deal with the data set. So in that case, in order to overcome that, the behaviors, the regularization, there's something always you have to think about it. So you can reduce the complexity of the model that you want to assume. Or the second thing is that you want to control the magnitude of the parameters that you have that. So I will include that things in our objective functions. So that's, we call it regularizations. Okay, so this, I mean, any questions so far? So far so good?
Yes.
Okay. So probably you guys can take a look at the Jupyter notebook that I posted it. So I mean, how do the models, the approximating models change the behaviors when we change the magnitude of lambdas, right? That's okay. But there are some other regularization techniques that I want to mention. So the first thing is that, so let me see, overfitting is it's occurring when you have number of errors and number of data points, right? So one way we can increase the number of data set. So that's why having a big data set is so important. If we have a big number of data set, that's the easiest way, or I mean, not easy, just natural way that we can, since we have, if in that case, this one is way bigger than number of unknown parameters, right? So the model will generalize things. I mean, this one is easy to say, but in real life, it's really extremely difficult to collect the many data set, or very expensive. So the second way that we can think of is data augmentations. What do you mean by augmentation? I'm going to explain it. So the simplest way to reduce the overfitting is to increase the size of training data set, right? So it's related to big data set. But again, I would say that is having an extra data set is probably very expensive. So let's think about, say we have this kind of cat figure, I mean the image. In order to have more data set, so we have to probably go to the internet, or you have to go out and to find the cat to take a picture of them. Right, that's the first way that we can do. Or, I mean, another or smarter way that we can think of like this. I mean, these are the same figures, and I gave some variations. I just here, how do I say, I flipped it, and I like, this one is like, let me say, I mean, this kind of figures. And here, I would say I just rotate it. So in image, you can just flip it and rotate it and translate it. You can do a lot of image using the processing to get more variations. Again, in this process, actually, we don't have to take a picture of a cat. We don't have to take the picture of extra cat. So here is, I mean, the thing is, these images, we can treat them as new data set, right? So we call it augmentations. And it's like working as like increase the number of data points. Does it make sense? So I really highly recommend, whenever you feel like you don't have enough number of data or training data set, think about the first thing is think about the data augmentations. It's extremely effective, actually, when you deal with the, yeah. And another, I mean, here is another example of that. And these are the, I guess, this data set with handwritten digits, and you can shift it, and you can share it, and scaling, and rotate it. You can many other operations you can apply it, and you can treat them. Actually, all of them are the same, but you can treat them as a different inputs. I think another one, and this is the last one in here, is different regularization techniques that I want to introduce here is early stopping, which means when you see the performance of the validation set is getting worse, just immediately stop the training of the models. What do you mean by that? Say for the, I will say you will do gradient descent, right? And as you keep iterating, repeat. So say here we started, and yeah, I mean these are the randomly initialized unknown parameters, so the errors probably is large. And as you keep updating it, it gets smaller and smaller, right? And around this point, if you start to observe the errors or loss functions on the testing data set, if you start to see increasing, you stop here. Because we believe that up to this point it's good for the generalization errors, but around here it's doing too much. Right now it's a kind of, so we want to avoid this kind of overfitting problem, so we will stop here, but it's a early stage, so we call it early stopping. So early stopping is very effective, especially in deep learnings. Does it make sense? So if you think, say, just you will set the for loop, like say from, I don't know, maybe like that. And this is not a smarter way. You have to, each iterations, or you have to plot the training errors and testing errors, and you have to decide whether you want to stop, you want to early stop, or you want to continue. You have to make decision on every iterations. And that's another regularization method. And the last one is a dropout, and is in Euronet. But I'm not going to explain what the dropout is at this moment. Probably I will have another chance to explain it for. So this one is another method for the regularizations.